we work on more on, we are a quantum cryptography group and we work more on quantum information or optical quantum information in that sense. So it has a flavor of quantum optics and quantum information. So as far the broader domain is concerned, this is a bit different from whatever is discussed means in the talk so far. So the basic Hamiltonians are similar, means the tools are similar, but the flavor of this talk will be a bit different from what has been discussed so far. So I'll talk about non-classicality or the states which does not have any classical analogs and their applications and how they appear and what connects quantum optics and quantum information to the PT symmetric community. And this will be in continuity with my talk in ICTS of in the previous edition of the similar conference, where I stressed that in quantum optics, the non-hermiticity is very common and open quantum system actually connects quantum information, quantum optics, and PT symmetric system. So in the same line means it's a more generalized results will be shown here.
Anirban, you may want to do a full screen of your slides. It's probably not in full screen right now.
Okay.
Yeah,
so
perfect. Thank you.
So the broad outline of the talk is that first I'll give a single slide on basic idea for PT symmetry and non-classicality for the completeness, and then we move to open quantum system, how open quantum system connect PT to quantum optics and quantum information. And then there are two parts actually of this talk. One discusses about quantum geno-antigeno effect in a system with two cavities which are connected and also connected with bath, and another system which is a three-level atom, and the effective Hamiltonian of that three-level atom will be reduced to two-level atom. So those two systems, and in those two systems, how the non-classicality appears and what happens to the non-classicality once we are in PT symmetric phase and if we go to PT symmetry broken phase. So to begin with, I'm describing PT symmetry in nutshell, but this is something which is not needed because the conference is already in last day and many people have defined PT symmetry. And so what P does and how P transforms and how T transforms the things we already know, but in what follows, I'll use the whole things in terms of second quantized annihilation and creation operator. And in quantum optics, it's very common that you describe the field in terms of annihilation and creation operator. So this transformation will describe in terms of P, and T will describe in terms of annihilation and creation operator, and we'll see that T reduces only to transform I to minus I. And PT symmetric systems have found various practical applications in context where I want to talk, means like in the domain of quantum optics and quantum information. So for example, we cite some strong articles, like it is related to magnetically induced transparency, reflectionless PT symmetric materials at optical frequencies have been developed. PT symmetric optical switches have been proposed. Single mode PT lasers exist from 6-7 years. So there are many proposals and some experimental realization of PT symmetric thing, and in the domain of broad domain of quantum optics. So what makes quantum optics? So there are three kinds of optics. One is the classical optics. In classical optics, the atoms are not quantized, as well as the electromagnetic field is solution of Maxwell's equation. So so we are interested in atom field interaction or matter field interaction. So neither matter nor field is quantized, then it's called classical optics. In the domain of semi-classical optics, atom is quantized, but the field is not. In the domain of quantum optics, both are quantized. So atom is also quantized, and it's a necessity. Means you cannot describe such phenomenon without introducing this notion of field quantization. So then in quantum optics, there is a strong notion of non-classicality. So in my title also, there is a non-classicality. So before I proceed, it's important that we understand what non-classicality is and what quantum optics people or quantum information people understand by non-classicality. So there are many ways to look at non-classicality. There are many witnesses, measures, etc. But the fundamental definition which we follow is that a non-classical state is one which does not have any classical analog. So how to see that? So the state which we consider to be closest to classical is a coherent state. A coherent state is a minimum uncertainty state. It's a displaced vacuum state. So in the sense that it's a minimum uncertainty state, it's the closest to classical state, because a classical state will not have any kind of uncertainty. Now, if a state can be written, density matrix rho can be written as mixture of coherent states, then it's called classical. So if it cannot be expressed as a mixture of coherent state, then it's called a non-classical state. So we write it like integration, like a rho is integration over p alpha, ket alpha, bra alpha, d2 alpha, and then for all the non-classical states, p become negative. So if p is positive, the state is classical, and p is negative. So that's called Glauber-Schroederson p function. But p is not measurable directly. Since p is not measurable directly, many operational criteria has come. Like negativity of Wigner is also a manifestation of Wigner function, is also manifestation of non-classicality. So whenever Wigner is negative, p must be negative, but the other is not true. So there may be states like squeeze states where p function is negative, so it's non-classical, but Wigner will fail to detect this non-classicality. So there are many weaknesses of non-classicality, but these are not measures. So there are measures too, but p function can, but these measures are not unique and they are not monotone of each other. So what kind of measures we have? So like one measure is a distance-based measure, that how far is the state from its nearest classical state, but the number of classical states is infinite, so you need to optimize over a infinitely many possibilities, which is practically impossible. So there are many such measures of non-classicality, and as I mentioned that in this work of ours, which is not related to PT symmetry, we have shown that they are not monotone of each other. So we may have this kind of plots, and the state A may be, so this side is one measure, this side is one measure, and state A and it's not a linear plot. So state A may be more non-classical by this measure, but state B is more non-classical by this measure. So there are practically many issues of non-classicality measure, and one nice thing come with Asboth. So Asboth told that if I have a beam splitter and I send a non-classical state from one port and vacuum from the other port, then the output will become entangled. And there are, in quantum information, there are many measures of entanglement, and they can be then used to find out the quantitatively measured non-classicality. But non-monotone problem will still remain. But he can, this idea can transform non-classicality of a single mode into entanglement in two mode, and then entanglement measure can be measured. So this will use for our work. So non-classical states don't have any classical analog, as I mentioned, and consequently they are essential in achieving quantum, not superposition, this will be quantum supremacy. So it's a typo. So in quantum supremacy, so Google has claimed that they have achieved a quantum computer which can do a task which classical computers cannot do in reasonable time. So all this quantum, if you have a quantum information or quantum computing, if you have a claim that something cannot be done in the classical world, so there must be some resource which you have used which does not have a classical analog. So non-classical states are extremely important for quantum information. A nice example is entanglement. Entanglement does not have any classical analog. So you can do tasks like teleportation, which does not have any classical analog. So there are many recent experiments like LIGO, through which gravitational wave is detected. So that's a Michelson interferometer. In one of the port, we have given squeezed vacuum state, which is a quantum state or a non-classical state. So satellite-based QKD experiment of China or Google's quantum supremacy claim, everything requires non-classicality. So that sets the motivation that why we are interested in non-classicality. Now, rest of the talk will be about two of our papers mostly. So the first one is interplay between non-classicality of PT symmetric in an effective two-level system with open system effect. So open system effect, actually, when you are working in closed system, then the dynamics and then everything is a standard. So only the open system effects introduce non-hermiticity and then allows you to find out the condition for PT symmetry, and open quantum system itself introduces the noise. So normally in quantum information, especially in quantum cryptography, we see the effect of noise through cross operators. So there are different noise models, and for each noise models, already constructed cross operators are there, and it's a standard mathematics how to construct those cross operators. So I'll talk mostly about different effect of different noise on PT symmetry, PT symmetric region and PT symmetric broken region. So we'll see the quantum Genome effect and non-classicality in a PT symmetric system of coupled cavities. So this will be a system where there are two cavities which are interconnected and both are connected to bath, but the baths are independent. So the cavity 1 is connected to bath 1 and cavity 2 is connected to bath 2. And this system will be a 3-level system, which is effectively under certain conditions will reduce to a 2-level systems, and the 2-level systems can be think of as a qubit, a quantum 2-level system, and then we'll find out its eigenvalues in which condition it is PT symmetric and what happens to the non-classical properties when we move from PT symmetric region to PT symmetric broken region and allows noise to work in the system. So noise is the real problem in achieving big quantum computers, but noise also gives the window to connect quantum optics, quantum information, and PT symmetry. Okay, so this is something, since I'll work on a 3-qubit system, which is, a 3-level system, lambda type 3-level system, which will be reduced to an effective Hamiltonian of a qubit or a 2-level system. So here I just to recollect a general parity operator in 2x2 space, the space in which our system will work from Bender's paper. The P and the PT symmetric general Hamiltonian looks like the equation 2 here. So this sets the background, and now I am in the physical model of 3-level system. So this is by the shape you can see that this is a lambda type system, and this is a 3-level systems 1, 2, 3, and delta 1 and delta 2 are the detuning. These are the coupling constant G, capital Z and J. So for convenience, I will consider that lowercase g and uppercase g is equal, and J will be connected with another function called omega. So how to look at the Hamiltonian? So these are like free field part, and these are the interaction part, and here these lambda 1, lambda 2 are detuning, and small g and capital G are Rabi frequencies of the two optical fields. Omega prime is the coupling strength due to the RF field. The phase phi can be controlled by the adjustment of the relative phase between RF field. So this is the system. Now, this system is not, of course, PT symmetric. So I want to reduce it to a 2-level system where working it is easier, and also to look what is the condition for going to a PT symmetric system. So we set up, as I mentioned, that the coupling constants are equal and the detuning are also equal. So that makes and introduce a new notation, a new omega, which is delta omega prime upon G square. So by assuming this equal population gain and loss rates associated with level 1 and 3 in the previous diagram, we get an effective Hamiltonian, and this is the effective Hamiltonian. And you see that now the effective Hamiltonian get rid of the factor, the state 2. So this has 2 levels only, 1 and 3. So since we have considered that loss and gain is equal in level 1 and 3, that helps me to reach here. So this is the effective 2-level system, and we can write this in this form. And finding out eigenvalue of this Hamiltonian is easy, and here you can see that 1 minus omega e to the power I phi is common everywhere, and you can take it like J. So I give a new parameter J, which is mod of this, and my eigenvalues are E plus minus is equal to plus minus square root of J square minus omega square. So now it's easy to check that what is the condition for real eigenvalues. So of course the condition for real eigenvalue is that J is greater than gamma, and gamma is my gain loss parameter because we have assumed them to be equal. So with J is this, the eigenvalues are real, and hence the system is PT symmetric when the effective coupling 1 minus omega e to the power I phi is greater than the gain loss gamma. The PT symmetry is said to be broken when the gain loss exceeds the coupling strength. So exceptional point, determination of exceptional point is easy. It is j is equal to gamma. So such that the eigenvalues e plus minus 0 are called the exceptional points, which is the borderline between the two regimes. So we started with a practical system, which is a 3-level atom, reduce it to an effective 2-level system. Our effective 2-level system is equivalent to a qubit for all quantum information people, and then we find out which side is PT symmetric and which side is PT symmetric broken region. Then we study the dynamics. So using the effective Hamiltonian, our 2-level system Hamiltonian, we write the Schrodinger equations and find out the non-unitary operator which will describe the evolution. And we find that j square minus omega square is appearing everywhere. So we introduce a new parameter, new name omega t. Now, usually in quantum information, you write ket xi as 1, 0 and ket 1 as 0, 1. But since there is no ket 0 here, so the ground state ket 1 is written like a conventional quantum ket 0 for quantum optics, and I write it like 1, 0 transpose. So it's a column matrix, it's a state vector 1, 0 at time t is equal to 0. Unitary operator is non, so I know how it will evolve. So in the PT symmetric regime, the xi pt after time t becomes this. So this is simply the unitary operator works on this and then leads to this state. So then there is a certain probability after time t to find the state in 1, although the state initially the state was in the ground state ket 1, and there is certain probability that you can find it in state ket 3. Now, if omega tends to 0, so omega tends to 0 means j square is equal to gamma square, which is my exceptional point. So if omega tends to 0, or that is j tends to gamma, we approach the exceptional point, and I can write the above wave function in exceptional points too. So equation 9 describes that. Okay. So for comparison, we also consider a case. So I just want to, in what follows, I want to consider the non-classicality of the wave function in PT symmetric region, exceptional points, PT symmetric broken region, and we also consider a Hamiltonian, which is Hermitian. So that's a simple Hamiltonian given in equation 10, where R has 3 components, R1, R2, R3, and delta denotes the Pauli matrices, X matrix, Y matrix, and Z matrix as sigma 1, sigma 2, sigma. Sorry, these are Pauli X matrix, Y matrix, and Z matrix. So for in quantum optics, quantum information, these are X gate, Y gate, and Z gate. So the eigenvalues of this Hamiltonian are plus minus magnitude of the vector R, and we claim that we are interested in a system whose eigenvalues are equivalent, or at least numerically equal to the eigenvalue of the PT symmetric system which we are considering. So by hand, I claim that numerically amplitude R is square root of j square minus omega square. And then we find out the time evolution operator, and with the same initial state, we find the state at time t. So we have states under different conditions for this 2-level system, and then we follow something from conventional quantum optics. So I mentioned that Asboth introduced a nice criteria for measuring non-classicality. So the idea is that from one side of a beam splitter, I'll give a quantum state. So it may be classical, it may be non-classical. And from the other side, I'll give a vacuum. And then the output will be an entangled state if the input other than this vacuum is non-classical. And if it is classical, then it will be separable. So we have many entanglement criteria, measures of entanglement. So we can apply those here and find out whether rho is non-classical, or rho, we can find out the rho input is non-classical, or how much non-classical it is by giving different measures. What can be the most general rho in single qubit system? It can be 1 minus pp x star, because this is unitary and trace is 1. So 1 minus p will make it. So this takes care of amplitude. So if you have a completely mixed state, then this x and x star you can make 0. And when you have a pure state, you will have x and x star. So anyway, so Asboth's idea was very interesting. So he transformed single mode non-classicality into a two mode entanglement and allowed entanglement measures to be, which is normally used in quantum information, to measure non-classicality. And he called, since this is not, actually he is not targeting measuring entanglement, he is actually measuring non-classicality. So he gave this as a name, entanglement potential. So now if I use concurrence to measure the non-classicality of this, then I will call it concurrence potential. If I use negativity to measure entanglement here, then I will call it entanglement potential. So there are other ways to find out the non-classicality. So some measures which can be used to measure two-mode non-classicality. So what we are going to do, that in the row input, I'm supposed to give different single qubit states. So what are those single qubit states? So in the context of PT symmetry, so I'll give this xi h ket xi ht, which is for Hermitian with the same eigenvalue. I will give this equation 9 describing the quantum state at exceptional point. I'll give this PT symmetric xi t. So all these are two mode state between 1 and 3, a single qubit state in that sense. So this will be given here. And we already know that if this is the most general state, so what beam splitter transform it to? So in all these cases, the coefficients are known. I can find out easily this matrix. So I'll know this state. And now once I know this density matrix at the output, I can apply different measures. So here is a measure. So rho A is partial trace. So we are familiar with that. If you have a bigger systems and we can trace out some of the stuff and find out the partial trace. So partial trace rho A is I PIA sigma IA, and sigma A, sigma B are projections on the corresponding state space with eigen values rho A and rho B. So this is conventional and much discussed, but in measurement induced disturbance, we introduce a new measurement operator sigma P, such that it is described in this way, that it's a measurement operator in both the subspaces in the tensor product space, because a first subsystem is described by the Hilbert space in the Hilbert space HA, and the second one is in HB. And now this operator is defined in the tensor product space HA tensor HB, and its rho is sandwiched between the operators, and we find out this. So this is interesting. So this is, we say that rho is a classical state if it does not change under this projection, under this measurement. So if this condition is satisfied, then it's classical. If not, it is quantum. So this is just a witness that it's classical or non-classical. It's not a measure. So how to convert it into a measure? So Luo and Rao with their collaborators converted into a measure, Q rho, and Q rho is defined in terms of mutual information, and I rho is defined as where S is von Neumann entropy of a state. So S is this S rho A is the von Neumann entropy of the reduced state, plus S rho B, the von Neumann entropy of the reduced state rho B, and then minus S rho, and this minus in mutual information of the state obtained by this operation. So now, since for a classical state, this condition is satisfied, that sigma rho is equal to rho, and then we can put it here, and the arguments are same, so this will be 0. So in the other sense, that Q rho will be 0 for a classical states, and Q rho will be non-zero for a non-classical states, and this Q rho gives you a measure of non-classicality in terms of MID. Similarly, we can use more popular criteria like concurrence, where concurrence is defined as we have defined in equation 17, and where lambda I are the eigenvalues of the matrix. So square root of rho bar. So what is rho tilde? Rho tilde is rho sandwiched between Pauli operators y. So we apply Pauli operators sigma y, the delta y in everything. All the qubits, means it's a 2 qubit system, and then we put it here. So that's a straightforward thing, and This varies between 0 for a separable states and 1 for a maximally entangled state. So the more it is, the more entangled is the system. So since we'll consider it as a concurrence potential, so the more will be the value of the concurrence in the output here. So the more will be the value of non-classicality in the row in. Then we want to see effect of noise in this, and there are different kind of noise. So one interesting noise is random telegraph noise. This model describes a qubit subjected to a classical source of random telegraph noise, that is a bar-stable fluctuation randomly switching between two states, and the rate of switching is given by gamma. So here the gamma is not my gain loss rate. So this is the same coefficient used, but this gamma is the switching rate of the random telegraph noise. So we can define a cross operator for random telegraph noise, and the beauty is that the random telegraph noise has two limits. So, and below a limit, it's a Markovian noise, and above a limit, it's a non-Markovian noise. So what is the difference between Markovian noise and non-Markovian noise? So Markovian noise, you can lucidly understand that something which does not have memory. So what happens to the qubit number 1 does not depend on what happened to the previous qubit or what will happen to the next qubit. But non-Markovian noise has a memory, and non-Markovianity normally shows the effect that normally in the noise, if the fidelity reduces, but if non-Markovianity is present, it can reduce, and then suddenly increase also. So that kind of turn in the fidelity is not observed in Markovian dynamics. So then there is a phase damping. So it does not affect amplitude, it just affect the coherence, and then there is a amplitude damping noise also. So there are for different noise, and for different noise I have different cross operators, and these are standard thing that how in open quantum systems and quantum information, that how we see the evolution of the state. So the density matrix rho evolves in this way in presence of the noise. So these are K1, K2, K3 are different cross operators that are describing a particular noise model. So rho is sandwich, and we sum over, and then we get that what will be the state.
Anirban, sorry to interrupt. You have about 10 minutes.
Okay, sorry, I'm going fast a bit. So we give the dense input states, and in noiseless channel, my rho output become rho, and then in different channel, what happens we have seen. So this figure is showing concurrence with respect to time when the state 1 is lit to the beam splitter. Left, middle, and right plots corresponds to RTN, phase damping, and amplitude damping noise. And that's not relevant for the conference, but this plot is more relevant for the conference. Here is a PT symmetric, all the blue lines are the PT symmetric regime. Then the red lines are PT symmetric broken regime. And this is in the, so we just send, I have a beam splitter, and the input state are different input states, and the input states are, the wave function at the exponential point, the ket xi at the exponential point, ket xi at the ket xi at the exceptional points, and the ket xi, the PT symmetric region, the Hermitian. So for all these things, how the concurrence is changing. So this is a concurrence potential, and you can see that apart from certain points, it's always showing non-classicality. So the non-classicality is oscillating, the amount of non-classicality is oscillating fast in the PT symmetric regime, relatively slowly in PT symmetric broken region, and it clearly shows means the variation of non-classicality is different in different region. So this is a similar plot with the MID, or measurement induced disturbance. So that leads to a set of conclusions. So the beam splitter provides an elegant way of analyzing the non-classical properties of the output state. The non-classical measures behave quite different in the PT symmetric region and PT symmetric broken region, as we have seen in these plots. So just compare the blue line and red line, and in this plots also. So there is a demarcation which happens in terms of non-classicality in PT symmetry and PT symmetry broken region. The result of PT symmetric systems are compared with the case when the time evolution is generated by a Hermitian Hamiltonian, and this allows us to demarcate the contributions to non-classicality from two types of dynamics. For the specific values of parameters used, it is found that PT symmetric dynamics shows enhanced non-classical features compared to the Hermitian counterpart. So that's easily seen here, that Hermitian is this lower plot, and you can see that non-classicality is much more in the PT symmetric region. So in both the plots, you can see that. Well, now we want to come to the second aspects of quantum genome. So the idea of quantum genome is interesting. So just first I go to classical genome. You think that the genome, when the simplest form of Genome's paradox, this tortoise is running and somebody is trying to catch him. The moment he reaches the point previously tortoise was, the tortoise go ahead a bit. The moment he reaches the second point, the tortoise is little, whatever be the speed, but it has gone moved from that point. So he will never be able to touch it. So an arrow is thrown towards a bird. So the moment arrow reaches the previous position of the bird goes a bit ahead. So every time, if you, the whole thing is that if you want continuously measure something, then you will, then certain different things happens. So if you think of a quantum state, a state vector is evolving. But if I do a continuous measurement, so if I have a polarization state and it's evolving like this, and I'm doing a horizontal vertical measurement. So if I measure this state, there is a high probability that I will get it vertical. Then I measure it again, it will be vertical. So if I continuously do measurement, I can stop the evolution or I can make it slower. So that's called quantum genome effect. And if the measurement leads to a faster evolution, then it's called quantum anti-genome effect. So what happens? So if you have an evolution UT and you can just a unitary evolution and you expand it and you for a short time, it can be reduced to this. This is the probability of evolution of a quantum states conditioned on the same initial and final state. So these are often used in many applications, especially in quantum information and counterfactual quantum cryptography. So this is a Chinese knot which is used in counterfactual quantum cryptography and using genome effect. So we are, without going to detail, so we want to see in genome effect in optical system. So I have two cavity. This is cavity with gain gamma 1 and this is cavity with the loss gamma 2, and here is two bath. So this cavity is represented by annihilation operator A1 and this is by A2. So as before, we write the effective Hamiltonian and find out the eigenvalue, and we can easily see that the eigenvalue can be both real and imaginary. So it is easy to define the PT symmetric regime and PT symmetric broken regime. Then there are two parameters, G and gamma. So here in this plot, we have shown the eigenvalues, real eigenvalues, which is a requirement of PT symmetric region, and the real part of the eigenvalue lambda plus minus is plotted as a function of the coupling strength G and gain loss rate gamma. So when I show it with respect to gain loss rate gamma, then G is taken to be 1, and so gamma is equal to G is the condition for which leads to this point. Means this will be lambda plus minus will be 0 and both will be 0. So this is giving the exceptional points. So exceptional point is seen here, and as secondly, when I show the plot with respect to G, then I have chosen gamma is equal to 1. So we have a well-defined PT symmetric region and PT symmetric broken region. So as the time is less, so I'm just moving a bit slowly. So we have started the dynamics and get the number operator. And now there is another way to look at the genome effect. So one such way is that, suppose we think of a coupler. So if a continuous interaction happens, then I consider one as the system mode and one as that interaction mode as if the measurement. So the system has been continuously measured. So if I have two optical fiber, so one mode is used for measurement and that is affecting the evolution of the other. So if the coupling was not there, then how the other mode would have been evolved, and in presence of the coupling, which is leading to the continuous measurement, how the other one is evolving, that leads to genome parameter. And we can use that genome parameter to see different things. So for different input states, like in the previous thing also, here we choose vacuum state, coherent state, noon state, and thermal state. And one is the A1 mode and the other one is the A2 mode. So we see that in the PT, this panel is for PT symmetric region and this panel is for PT symmetric broken region. So in one case, gamma is shorter than G, and the other case, gamma is greater than G. So this plot shows that more or less the two modes grow in the same way in PT symmetric region, but it's not the case in the PT symmetric broken region. So there, one is growing fast with compared to the other one. So this is the Genome parameter, which is shown in terms of the difference in the number operator, and you can see that in one mode we can see the positive effect, in the other mode we can see the negative effect. So what it implies that this is the one is showing Genome effect and the other one is showing anti-Genome effect. So one is evolving fast, considering the Genome parameter as positive, and one is going slow, indicating the negative Genome parameter. So we continue with the similar things, that here we are showing intermodal antibunching. So A1, A2 is indicative of intermodal antibunching, and this one is showing some squeezing and different squeezing. So you can again see that this is where G is greater than gamma, and here where G is shorter than gamma. So the color code is same, and one is defining PT symmetric region and one is defining PT symmetric broken region. So some squeezing parameter VA1, E2, and the difference squeezing parameters evolution as shown here, and plotted again dimensionless quantity gamma T, and a state is some difference is squeezed if the value of VA1 or WA1, 2, etc. are negative. So 0 is the parameter for coherent state, and these are showing squeezing. So non-classicality is observed, but the whole point is that the non-classicality, whether it is anti-bunching, whether it is squeezing, is different in the PT symmetric region and PT symmetric broken region. So you could have drawn a line from here at 1 and to indicate that, sorry, not in this plot. So in this plot, we can, this is gamma by G. So if gamma by G we take 1, so that will demarcate the PT symmetric region and PT symmetric broken region, and we'll see that the dynamics is different, absolutely different, that how non-classicality evolve. So this plots I'll ignore. I mean, this was to another system, which is not of course PT symmetric, but to show the Genome effect, that if one of the these fibers interact, and we can consider that it is interacting continuously, and the continuous interaction is leading to continuous measurement, and that leads to Genome effect. So I guess the time is over, so I'll stop here.
Thank you, Anirban, for this wonderful talk. So, any question, anyone? You can unmute yourself and ask. Okay, so if there are no questions, then maybe we should thank the speaker. So thank you, Anirban, once again.